Dr. Ince come up, Professor of Biomedical Engineering, the most recent addition to the team here, and I think he's just been a fantastic person to have. He's really pushing the field forward in different biomarkers for epilepsy and movement disorders, both passive biomarkers and stimulation elicited responsive biomarkers as well. But Dr. Ince.
Today I will try to share our experiences, our journey towards the identification of neurobiomarkers for the optimization of neuromodulation and neurosurgical therapy. As a person, as an engineer who spent years in the area of brain-machine interface, I would like to always present this slide for the gentleman, the Superman that I know, who suffer from spinal cord injury, and then these type of systems are supposed to initially help subjects who are locked in, and then try to record the neural activity and use that for communication and control. So another form of BCI or brain-machine interfaces could be simply clinically oriented or clinically tuned, in which we can once again record the neural activity, but in this scheme, rather than just giving a feedback or controlling a robotic arm, use that information to improve the diagnosis, build different types of therapy, optimize therapy, but from my perspective also to understand the mechanism of the disease. That's a unique opportunity, because the more or the better we understand the optimal or more personalized we can make the therapy itself. So, zombies. So I would like to share this interesting quote from this movie, World War Z. Mother Nature leaves crumbs. And I don't think it will be wrong to say, as researchers and scientists, we are observers of the Mother Nature, the clues that it leaves behind, so we can understand the disease. And in this particular scene, that this observation, key observation, helped them to survive, to treat or deal with the disease itself. So let's see what we can find, what kind of clues we can extract from the brain, understand the disease. So for those who are not familiar with deep brain stimulation in Parkinson disease, this is an FDA-approved therapy. Electrodes are implanted into the deep brain, and electrical pulses are delivered to suppress the motor symptoms, motor features. And as you can see in this particular video, one can see actually instantaneously the resolution of the tremor, resting tremor. But at the same time, the stimulation electrodes can be used to observe the neural activity that's done in the epilepsy practice. And recorded signals can be used to understand maybe the disease, or use it, like from my perspective, when I engage with this project, for the optimization of the therapy. So years back, almost 20 years ago, with industry funding, we executed a study in which we externalized the DBS electrodes, recorded local field potentials, the oscillations of the brain from subthalamic nucleus, and then tried to correlate it with the disease symptoms. Something that I observed, I still remember that moment, when I executed speckle analysis and look at the contact that had the maximum beta synchrony, as we observed in the previous slide. It also correlated with the contact pair that provided the best therapy to the patient, which was simply identified by the clinical nurse through a trial, through testing multiple contacts, or trial-based operation. And in 4 subjects, repeatedly, we observed the same pattern. I remember, sending a text to Aviva, and then with a goosebump, and then it was replicated by other researchers. Well, if these potentials can be now functionally used for the optimization of the therapy, let's see if we can, record them over prolonged periods such that they can serve, closed-loop neuromodulation applications. 3 to 7 years after the implantation of the electrode, when the patients came for battery replacement, we externalized the electrodes now from the chest and recorded the local field potentials. It turns out they are still there, and then it can be used in closed-loop applications, not for acute, but also chronic periods, chronic use. So the same strategy now can be utilized to understand how the pharmaceutical therapy actually kicks in, and then shows its clues or its patterns. Once again, another, industry-funded study, we externalized the electrodes and gave the patients a relevant medication, levodopa in this case, and asked them to give us a verbal feedback when they feel on. And here you can see the medication off and on state videos kind of highlighting the resting tremor. And what was remarkable, when the patient felt on, and then that verbal feedback not only correlated with the beta suppression, but also, a very unique enhancement in HFOs, high-frequency oscillation, reaching up to 350 hertz. And it turns out, actually, the interaction between these two frequency bands, the nonlinear interactions, can little tell us to predict how much they will improve. So giving us another clue or pattern that can be used to titrate DBS and pharmaceutical therapy in these patients. Well, optimization of stimulation contact, pharmaceutical therapy or medication. But no matter what, the efficacy of the DBS depends also on the location of the electrode. So Brian described this procedure very nicely. During awake surgeries, microelectrodes are penetrated, but obviously the neurosurgeon cannot see where the electrode is located, and we cannot just cut the brain and then look inside where it's located. So in order to account this type of brain shifts or caveats in neuroimaging, multiple electrodes are penetrated through a bang gun. There you go. So and then the electrophysiologist, neurosurgeon, then tries to interpret the recorded neural activity, as you can see up there, in the form of bursting neurons, and then kind of trying to figure out which track to use and at which step to locate the electrode. However, as Brian mentioned and Kai mentioned, it's kind of difficult to isolate individual neurons. There are so many technical difficulties. Based on the experience we got from the previous studies, we proposed, why not to use the brain oscillations? However, if you try to listen to these oscillations, they are below the hearing range. No one can actually extract relevant information from the signal. So through the support of National Science Foundation, we proposed a project and got funded to bring the AI into the intraoperative room almost like 15 years ago. And the idea was to record these potentials from microelectrodes, oscillations of the brain, from multiple tracks, and then do this real-time signal processing and give feedback to the clinician physician intraoperatively, just to see this information could be relevant for the optimization of lead placement. And it turns out in 80% of the cases, we were able to predict the decisions of the neurosurgeon. Simply that lead location was guided through imaging or by listening to the single unit activity. So we translated this system later through industry funding into real-time system to provide this type of feedback in real time. As you can see here at the bottom, a gaming laptop actually processing all the data in real time and feeding it to the clinical experts as a visual representation of the activity. But something very interesting happened during these studies, although it wasn't the intention. After looking at these pathological modulations in the territories of SDN, we noticed that if you put these two groups, two motor phenotypes of Parkinson's disease, tremor dominant on the left, PIGD on the right, it turns out they have differential electrophysiological footprints in the territories of SDN. And in particular, in the dorsal territories, TD patients had high-frequency oscillation, excessive high-frequency oscillation, around 220 hertz, which didn't appear in the PIGD group. And the frequencies were also differential. And the phenotyping in Parkinson's disease was defined since early 90s, but there were no electrophysiological correlates. For the first time, by luck, we actually identified these electrophysiological patterns. And then it turns out they correlate also disease severity. And we got funded by NIH now to explore these potentials in more detail with the segmented electrodes and see if we can optimize the therapy for these individual motor phenotypes so to deliver the personalized therapy. This is our research group. Although it's so effective, it's remarkable, we still don't know how DBS works. So the frequencies above 100 hertz are quite effective. That's what we know, but we don't know why. So one of the caveats in the field in studying stimulation-induced potentials is related to the technology. So whenever you stimulate the amplifiers, they get saturated. It's difficult to see the signals. So we work with neurotech vendors to record neural activity during the stimulation. On the top left, we are seeing actually a stimulation period in STN with 2 microelectrodes, one stimulating, the other one recording. And we observe interesting, responses, evoked responses, and then oscillating activity and dampening. And initially we thought this is an artifact. Then we repeated the same experiment out and in STN just to see if they are artifact or not. If they are artifact, they will appear everywhere. It turns out this was very specific to the STN, what we call today evoked resonant neural activity. And when we stimulate the same structure with a therapeutic frequency versus non-therapeutic one, we observe that the therapeutic stimulation frequency also induces HFO in the STN. And here is the interesting relationship. On the top panel, we are looking at the pharmaceutical modulations of LFP when levodopa was given to the patients, inducing HFOs, suppressing beta. And at the bottom, you are seeing electrocytical modulations. They are overlapping almost 1-to-1. They are both suppressing the beta. They are inducing HFOs, maybe giving us a unique clue about how mechanism of TBS, how it works, and there's an interesting overlap. So now why not to try the same recordings with the DBS electrodes? And it turns out we can capture these evoked resonant activities from the directional leads, see the topographical distribution, and we can tell which contacts are in and out of STN, which is remarkable. But what is more important to us is when we record the same potential while the patients are awake and asleep during DBS surgery, we could record them. So one of the caveats in the field with LFPs or single unit activities is that when the patients are going through a sleep surgery, it's very difficult to observe these potentials. It's difficult to isolate them. It turns out ERNA can be captured both in awake and asleep states, suggesting that now we can do actually sleep surgeries with electrophysiology. So this is very unique, and then hopefully in the near time we will run this clinical trial through real-time intraoperative observation of evoked resonant activity, both from microelectrodes and directional electrodes, to optimize or personalize the DBS surgery and DBS therapy. And obviously work with neurotechnology vendors, leaders, such as Cadence, to translate this not only to the intraoperative environment, but also towards the chronic use. So hopefully we can advance to the next chapter. So I will switch here. It might be a little bit, challenging, but I will try to do my best. So let's search for the same clues or same patterns in the epilepsy or intracranial EEG. So as the previous speakers described, in epilepsy, in focal epilepsy, refractory epilepsy, it's very critical to identify the seizure onset zone, such that a surgical therapy can be applied, or like for instance, the epileptogenic zone can be removed, and neuromodulation therapy can be utilized. And for these purposes, intracranial EEG, Surgeries is used as a gold standard. The process includes implantation of multiple electrodes and observation of the multiple seizures, such that we have enough evidence to call one particular or multiple areas as the regions that are generating the seizures. But one of the caveats is a time-consuming process. The patients need to spend from days to weeks in the OR or in the EMU, so it is difficult to minimize the risks if the recording period is too long. So high-frequency oscillations, similar to Parkinson's disease, but with a different, temporal and spatiotemporal footprint, can be used for the identification of the epileptogenic regions. But visual identification of these patterns in multi-channel data, prolonged data, it's super difficult. So that's why we need robust, reliable AI tools. So we tackle this problem and we establish certain AI tools through which we can identify what we call stereotype clusters of high-frequency oscillations. What do they mean? What we observed was eloquent cortex was generating HFOs, so normal tissue can generate these HFOs, but they are quite arbitrary waveforms in broadband, and then the seizure onset zone generates stereotypical waveforms like tics, but with random intervals. So we tried to capture these through intraoperative recordings, And then we try to build an AI tool that can mimic whatever the experts, clinical experts are doing, inspecting the neural data and identifying relevant physiological patterns or pathological patterns, more importantly, in the presence of artifact. And this is something that has been ignored in the field. We always pick the best segment to do the data analysis, but in practice, in clinical practice, this is what you have. And you need to build an AI tool that can deal with this type of problems. So we established this tool and applied to intraoperative data. These are the waveforms that the AI learned and tried to extract the seizure onset zone. And intraoperatively, we were able to almost match the EMU decision quality or decision precision. So, and we could also predict those cases that are going to fail. So we recently published this study and now trying to translate this into a real-time application for rapid identification of the seizure onset zone. And similarly, we are trying to build a real-time system for the detection of these events intraoperatively on the EMU, such that the dynamic feedback can be given to the clinical experts. And here, actually, you are seeing the first version of this real-time system, processing the data and telling us where the seizures are likely coming from. So finally, we are translating now this hardware or this AI or fusing it with a next generation implantable device, wireless implantable device, Cortex implant, and doctors Miller and Worrell, they are using the same hardware with animals. And then here are the first studies that integrates these two devices, AI for me, and the other device is the implant itself. And the future will be the integration of these AI tools with next generation brain implants, also surgical therapies, such that we can deliver personalized therapy in terms of neuromodulation or surgical resection for the delivery of the best therapy, that best opportunities to these patients, such that they can utilize and have an independent life. Right. This is pretty much my presentation, and thank you all.
We recently visited Carnegie Mellon, and there were some researchers there that are transcriptomically analyzing different neurons and have demonstrated that different neurons respond differently to different frequencies. And I was wondering if that's indicating in some way the underlying neuron that's either causing the problem or fixing the problem, and whether that's an area that's worth pursuing in terms of the type of work that we're doing here. In other words, trying to understand which neuron is actually responding to the frequency. And maybe there are different frequencies even in the same disease that might help.
That's a great question. So what we know, and then Brian presented nicely, the individual neurons, they have a certain characteristic in the territories of STN and GPI, and their distribution kind of defines the symptoms, the severity of the symptoms. But to me, whatever we are observing in terms of evoked resonant activity or the efficacy of DBS, I don't think it relies or it depends on individual neuron, but more to the circuit or the structures that are involved in the generation of these pathological activities. Probably the oscillations that we observe, HFOs, beta, and the others, they are pretty much representing the circuit itself. It went from a healthy state to a pathological state. And one of the key observations is excessive synchrony in the form of beta, in the form of HFO. And if you look at the neurons, they are bursting, periodically bursting. So why these frequencies are efficacious? So this is the neurobiomarker evidence that we have. Whenever you stimulate, you can modulate them to different frequencies. And we don't know what is the healthy frequency state. Actually, we didn't know until we went to a conference in Minneapolis. Dr. Vitek group was presenting recordings from a monkey, which became Parkinsonian, a model, obviously, that they induced. However, they got the same recording before the induction of the model, so in the healthy state. It turns out, when the monkey was in the healthy state, there were HFOs around 350 hertz, which we induced either with stimulation or pharmaceutical therapy. But when the monkey became Parkinsonian, it shifted down to 250 hertz. So the frequencies, the amount of excessivity or synchrony of these oscillations, they give us clues actually about the disease state and its mechanism. Right? Thank you.